Okay, we're good. So, radiation, and this is going to be sort of chapter 1, right, of this, the last two chapters, or the installments on radiative heat transfer. So, right, as I said, radiation, unlike convection and conduction, does not require a medium through which to propagate thermal energy. So before we get into a whole lot more, let's go ahead and plant our flag here and state the following definition of thermal radiation. Okay. Energy emitted by any body at a temperature exceeding absolute zero and we'll go ahead and leave it at that. So, right, the thing here is that any body at a temperature exceeding absolute zero, that means effectively anything that we encounter, no matter how cold it is in terms of our subjective sense, is actually throwing out thermal energy. Right? A block of dry ice is actually actively bombarding us with electromagnetism in an attempt to heat its surroundings up. So that's the other interesting difference between radiation and the other previous two mechanisms, is that heat transfer does not only go right from a hotter body to a colder body, it goes from any body to all other bodies. So what we'll see, though, is that we managed to hold on to the second law of thermo once we start adding up all of the different recipients of that thermal radiation. So the process of thermal radiation is effectively this. Right? When an object, whether it's a gas, a liquid, or a solid, is at a high temperature, right? Lots of thermal energy. We talked about before, that tends to manifest as molecular vibrations. Okay. If it's a gas or if it's a fluid, those molecules are in an unstructured sort of soup. And if it's a solid, then they're in this lattice framework. But in either case, those molecules are going to be exhibit a lot of kinetic energy, okay, whether in the form of vibrations or random motions. So, molecular vibrations, which by action of Ampere's law will create a magnetic field. Okay. And this changing magnetic field will, by action of Faraday's law, create an electric field. And so it's no coincidence that we've got magnetism and electrification here, or electricity, what we call electromagnetic waves. The idea is you have this sort of out of phase induction of magnetism and electricity that are created by these molecular motions. So, right, this is one of the two ways of viewing radiation. We'll go ahead and quickly outline those two ways to view radiation from a physics standpoint. The first is this idea of electromagnetism that we just outlined above, which is the propagation of energy via waves. So Wave theory is a big part of the way we consider light to behave, optics, all the way to coastal wave dynamics. Right, the same sort of theories govern all of these sort of notions of waves. Those and the linchpin of those being that energy is transferred not by pushing energetic mass, but by communicating energy through a space. The second sort of predominant theory is quantum theory, which envisions that radiation is transferred, radiative heat transfer occurs through the propagation of photons, or what are known as quanta, which are actually energetic particles. Okay, so it's important that we understand that there are two ways of viewing the same phenomena. Both of them are theoretically consistent and complete and pretty well accepted, but we are going to be focusing on the one that's based in electromagnetism, because this is the one that's friendlier to those of us who have not taken quantum theory courses. Right? So since we're dealing with electromagnetism, we got to spend some time talking about what we mean by waves in the sense of radiation. Okay. So waves themselves are described or defined by two terms: wavelength and a frequency. So we'll go ahead and define this guy as lambda and this guy as nu. Right. I should mention here that I really hate the fact that the book chose to use nu for frequency. I prefer omega, but to stay consistent with the book's definition, we'll go ahead and go with this Greek nu. Be careful, though, that you do not confuse this with kinematic viscosity. Right? Same symbol, two very, very different physical quantities being described. So the way these two quantities are related to one another is through the speed of light, where we'd say that the wavelength is equal to the speed of light divided by the frequency, where the wavelength is typically defined in known as microns, or mu-m, right, which are equal to 10 to the negative 6th meters. Frequency is defined in, you'll see it as hertz, 1 per second, or sometimes CPS, or cycles per second. And then c is, of course, the speed of light, which is equal to 3 times 10 to the 8th meters per second in a vacuum. Okay, so the idea is whatever this wave, and we haven't specified what exactly this wave is yet, right? This oscillating form of energy, whatever it's traveling through, whether that's air, water, vacuum, that choice of the medium through which it's traveling is going to determine exactly what the speed of light is. Okay, that's why prisms work. Right? They slow down, or you end up with refractive indices because the speed of light is different in one medium than the other. But for a fix, the idea is that c should be pretty much constant within that medium. This isn't changing. And so you have this inverse relationship between wavelength and frequency. In other words, if we go ahead and draw a quick little sketch here, go ahead and say this is This is X, Y. Let's go ahead and plant one nice long wavelength right here. So the wavelength is defined as, well, let's draw that. So we have a complete wavelength. The wavelength is defined as the distance from, right, crest to crest. And the idea is that a given crest is going to be moving at the speed of light, c, right? And so for a big wavelength like this, because it's moving at a constant speed, it's going to have a much lower frequency than, say, a higher frequency or a shorter wavelength wave, like the green one here. So if you imagine yourself as an observer, fixed right here, and these both traveling such that this crest and this crest are both traveling at the same speed, it is you're going to see a whole lot more full periods of this shorter wavelength wave in a unit time, which means it's the higher frequency. So the takeaway here is simply, small frequency, large wavelength, and small wavelength, high frequency. So the electromagnetic spectrum, right? Electromagnetic waves, which are what are responsible for transferring this energy, span the entire range of wavelengths. Okay, I mean down to from very very tiny like gamma rays, right, to all the way to these gravity waves that were recently measured using these giant optical facilities. Okay, so we're talking about everything from let's see, 10 to the negative 10th meters all the way up to kilometers, and that's just what we've measured, right? So we've got a huge range of different wavelengths, but we're only concerned with, in this course, a specific band of those. So let's go ahead and specify where the so-called thermal radiation spectrum lies in terms of the range of wavelengths. So this is probably a figure that you've seen before in physics courses, but bear with me, we'll go ahead and draw it. So if we've got wavelength on the x-axis here, 10 to the negative fourth, 10 to the negative third, 1, 0, 2, 3, 4, 5, 10 to the negative squared, 10 to the negative 1, 1, 10 squared, third, 10 to the fourth, 10 to the fifth. Okay, so this is the range of sort of common wavelengths in microns. And basically everything that is below 10 to the negative fourth microns. Okay, so we're talking 10 to the negative fourth times 10 to the negative sixth meters, so 10 to the negative 10th meters. This is the range that we call gamma rays. From 10 to the negative fourth to 10 to the negative second power. And these are X-rays. 10 to the negative second up to around let's go ahead and this is going to be 0.4 is the limit right here. So 10 to the negative second up to around 0.4. This is what we call ultraviolet. from 0.4 to 0.7, this is visible light, okay? From 0.7 up to around 100 microns, this is infrared. And from 10 to the squared up, we call this microwave. And I should mention that, right, some of the more common technologies that we use, right, your cell phones, the Wi-Fi chips in your card. If you think about like 2.4 gigahertz, right, that tells you the frequency of those particular electromagnetic waves. And what we would find is that 2.4 gigahertz is 2.4 billion, so times 10 to the 9th hertz. If we wanted to figure out the wavelength of that, we would simply divide that into C, or 3 times 10 to the 8th. And what we would find is that we end up with approximately 0.125 meters. That is the wavelength of your typical like 2.4G Wi-Fi card. Is roughly a tenth of a meter, so we're talking like 4 inches. Okay, and so that's up in this range where we have radio, Wi-Fi, cell service, etc. So the range of wavelengths that we are interested in terms of thermal energy, okay, the thermal band, is located between 10 to the negative first and 10 squared. In other words, this band right here. So it spans part of the ultraviolet spectrum, all of visible light, and up to the limit of infrared radiation. Okay. Go ahead and highlight that too. Interesting little to diverge here for a moment. Right, this sort of computation is how you design antenna for radios. For example, I'm sure a few of you probably have GoPros at some point. How many of you have noticed that as soon as you put a GoPro underwater, it stops working with the wireless signal? Anyone observed this? Well, if you take an old piece of TV, like coax cable, and you strip off half a wavelength, in other words, if a wavelength is 12.5 centimeters, strip off about 6.25 centimeters of insulation from that, and tape it to the back of the GoPro, and leave the other end 6.5 or 6.25 centimeters stripped out of the water, then basically you have a half wavelength antenna receiver and transmitter, and it'll actually successfully transmit that Wi-Fi signal underwater. Right? So this is the way that you design antennas for specific frequencies, is based on the length of that sort of conductor relative to the length of the wave that it is trying to transmit. And so you have things that are called like quarter wavelength antennas, half wavelength antennas, full wavelength antennas, and that's an example of a half wavelength antenna. Heat transfer, where you learn to use a GoPro. Okay, so the idea here is that if thermal wavelengths or thermal radiation encompasses this entire range of wavelengths, like it's a pretty small band in the scheme of things, considering this is a logarithmic scale, right? But we're still talking about 3 orders of magnitude. Okay, so wavelengths all the way from 10 to the negative 7th meters all the way to 10 to the negative 5th meters. And there's nothing saying it can only contain one wavelength at a time, right? You're not going to have pure wavelengths unless you're dealing with a laser. And that's the idea with lasers, is they're highly coherent. a very tightly packed group of wavelengths at one, or tightly grouped series of waves at one wavelength. But in general, right, thermal radiation occurs by adding together a bunch of different wavelengths, and you end up with this mess of incoming waves, which leads to what we call a spectral distribution. So thermal radiation can involve numerous wavelengths superimposed on one another, and this leads to spectral distributions. So a spectral distribution is going to be something that looks like so. You'll have wavelength on the x-axis, and you'll have perhaps E, which we'll call our emitted power. We'll go into this in just a second. And you'll have some sort of plot that looks like this. Now what this is going to tell you, right, is essentially the amount of energy contributed by each wavelength. Okay. So let's halt for just a second. Let's sort of regroup and say, okay, what have we established so far? Facts so far. Things we've established are that thermal radiation travels at the speed of light requires no medium in order to propagate. And travels as waves with wavelengths between approximately 10 to the negative 7th meters to 10 to the negative 4th meters. I guess that was 10 to the 10 to the negative 4th. So I want to change tracks here for just a second. Right, that's a broad kind of overview, a qualitative description of what radiation is, how it fits into the broader scheme of electromagnetism, physics, optics, etc. Okay, let's talk quickly about some definitions. Radiation is chock full of definitions, and these are some things we're going to need to get straight early on, and it's going to sound like I'm just making up some of these words. Okay. So some of these we've already seen in chapter 1, right? Like E, we're going to define as the emitted or emissive power in units of watts per meter squared. And this is basically sort of in words, this is the energy that is being actively emitted by a body at a non-zero temperature. Okay. I've chosen this phrasing deliberately, right, where I say actively emitted, and that this is the radiation that's actually being generated and cast out by the thermal energy of this body, as opposed to energy that's, for example, being reflected off of. So, continuing on, G we define as irradiation. in watts per meter squared as well. And this is the sum of all energy incident upon a surface. So whether that's the sun shining on an object, a heat lamp glowing next to it, sticking something into the microwave, or shining a laser at it. Right? These are all ways in which you are bombarding an object with radiation. And so all of that incoming energy, right, is encompassed by this irradiation term. So pictorially, it helps to draw a figure here. We'll say this is some surface at a non-zero temperature. It is actively emitting some heat flux, E. And we'll go ahead and say we've got some incoming irradiation, G. Okay. Now, what happens to this incoming radiation is where things get a little bit trickier. The idea is some of it is going to be absorbed, some of it's going to be reflected, and some of it is simply going to be allowed to pass through the object. So we have three parameters that we need to establish. There's going to be, like I said, some of it is going to be reflected. So we'll go ahead and call this G ref, or G reflected. It's defined by G ref is equal to, again, rho times G. I don't know why they're recycling symbols on us, but it's, again, rho here is not density. So make a note that when we're talking about radiation, rho is our known as the reflectivity. Okay. As I said, then whatever isn't reflected is going to go into the object, and from there it is either going to be absorbed, right? That is the irradiation that finds its way into the object and acts to increase the amount of thermal energy actually in that object. We'll go ahead and say we'll call G sub abs for absorbed, and this is equal to the product of alpha times G, where alpha is defined or is called the absorptivity. And finally, whatever isn't absorbed or reflected is simply going to pass through the object. And for example, if you think about a pane of glass, right, the idea is that sunlight hitting the pane of glass, some of it's going to reflect off, end up with reflections, glare. You might end up with a little bit of absorption. Chances are that a pane of glass has direct sunlight on it is going to be a little bit warmer than one that's in shadows, but most of it is simply going to be allowed to pass through. Okay. And so that, we're going to go ahead and draw in red because I'm using red to establish energy paths which ultimately leave the surface. We would call this G transmitted. This is going to be equal to tau times G, where tau is known as the transmittivity. Or, sorry, that's not the correct word at all. Transmissivity. So some of these, it sounds like they're just meaning transmissivity. Yes. Okay, so now that we have these different energy paths defined, there are two more primary sorts of energy flux terms that we need to define, right? E and G, these are both take the form of energy flux, right? Watts per meter squared. The energy actively being shed, all of the incident energy. There's also going to be this component we call J, which is known as the radiosity. Also watts per meter squared, and where J is defined as, we'll avoid a mathematical definition right now. This is essentially the sum of all radiation leaving a surface. Okay, so this includes E for starters, right? That's the radiation that's being actively emitted, as well as the reflected radiation. And if this surface has some transmissivity, that is, if some of the irradiation is passing through it and coming out somewhere else, it's also going to include the transmitted radiation that's allowed back out of the body. So we have three different sort of sources, or three different types of energy that's leaving the body. And all of these get summed up into J. And finally, we've got Q double prime equal to J minus G watts per meter squared. And this is known as the net radiative heat flux, and is essentially the difference between outgoing and incoming radiation. So this will be positive if the body is ultimately shedding more radiation than is coming in. Okay. So, right. So we can see here that these are all just sort of bookkeeping tasks. Probably the most complicated part of this is sort of understanding this idea of reflectivity, absorptivity, and transmissivity. And these have a lot to do with what the actual material that is being irradiated or which is radiating is. So I want to talk about sort of three important subclasses of materials, or types of media. Okay. So obviously, right, radiation can travel through a vacuum, which is essentially has perfect transmissivity. Right, the vacuum shouldn't be absorbing any radiation or reflecting any of it. But once that radiation actually hits something, what it does from there in terms of reflection, absorption, and transmission is going to have a lot to do with what's known as the opacity of that material. So if we have what's known as a transparent surface, this is one for which tau, the transmissivity is approximately, that the absorption is approximately equal to 0, and tau should be essentially high. In other words, it doesn't absorb much radiation. Any radiation that does find its way past the reflection should basically be passed through. Good examples of this include high-quality glass, optical glass, right? Camera lenses, things that are designed to attenuate light as little as possible, or attenuate electromagnetic waves as little as possible. They are transparent to those waves. So a good way to remember these is in terms of the way we see objects, because visible light is entirely within that thermal spectrum. So if it looks transparent to us, then that basically means it is transparent to that band of wavelengths. Semi-transparent surfaces are ones which have, right, a moderate values of tau and alpha. In other words, some of the light is going to be absorbed, or some of that radiation will be absorbed, and some will be allowed to pass through. Think about, I don't know, smoked glass, or the behavior of sort of semi-transparent silica, and things where there's a vague sort of transparency. Some light finds its way through. It's not necessarily reflecting all of it, but the idea is if you put that thing under a light for long enough, sure, you'd be able to see sort of glowing from the other side, but it would also begin to heat up in a way that a high-quality optical glass wouldn't. And that's a sign that it's absorbing some of the energy that's incident upon it. And then finally, opaque surfaces in which tau is approximately equal to 0. That is, any radiation that is not reflected is almost immediately absorbed right at the surface of whatever that radiation is incident upon. The example, the reason that this is important is, imagine, right, you're out sitting out in the sun. Hard to imagine with the weather we've been having, but out on a particularly sunny day, right, and you end up with a sunburn, right? You're not getting roasted all the way down to your vital organs by the sun. The idea is that radiation is incident on your skin, which has a very high absorptivity. Okay, you are effectively it's an opaque surface, which means those wavelengths, that radiation hits your skin and immediately gets absorbed and doesn't penetrate any further. So your skin gets roasted, your liver doesn't get roasted. Okay. And so a few characteristics here is that we're going to be focusing largely on opaque surfaces in this class, right? Transparent, semi-transparent surfaces are things that we're not going to be spending quite as much time on, but we will mention them in passing. And so an important definition is that, right, if the sum of the radiated energy, the sum of the absorbed energy, transmitted energy, and reflected energy has to be equal to the total incident energy. That makes sense, right? It's an energy balance. And what this means is that if G must equal the reflected energy plus the absorbed energy plus the transmitted energy, that means that rho plus alpha plus tau must equal 1 in general. And in the specific special case of opaque surfaces, because the transmissivity is 0, then rho plus alpha must be equal to 1. So all the light is either reflected or absorbed. So quick example, and we'll go ahead and wrap this up until Friday. I want you to imagine that we've got an opaque metal surface that is being irradiated by a laser. Laser radiation with an irradiation density of 1 kilowatt per meter squared. At the same time, it's at some non-zero temperature, and measurements confirm that it is emitting. We'll go ahead and actually we'll treat this as just one surface. Let's go ahead and say it's just one surface of the plate is emitting energy with a flux of 10 watts per meter squared, and tests confirm, right, that the particular type of metal we're considering has a reflectivity of 0.6 and an absorptivity of 0.4. Okay. So from these quantities, can we go ahead and find the amount of reflected radiation, the amount of absorbed radiation, the radiosity, and the net radiative heat flux? This is pretty simple. It's quite literally arithmetic. So I'm going to give you guys a couple of minutes and we'll see if everyone's on board. Anyone have G-ref, the reflected radiation? Exactly. So this is going to be equal to rho times G, or 0.6 times 1 kilowatt, which is going to be, per meter squared. Should be 600 watts per meter squared. Okay. The absorbed rate, or the absorbed flux, G, 0.4 times 1 kilowatt per meter squared, which will work out to 400 watts per meter squared. So from this, what should be our number for the radiosity, J? 610. Right? Because we've got the reflected radiation bouncing back off from the laser accounts for 600, plus it's emitting 10 watts per meter squared of its own thermal radiation due to its temperature. So this would be G ref plus E. It's going to work out to 610 watts per meter squared, which means our net radiative heat flux, J, minus G, right? It's just going to be 610 minus 1 kilowatt. So 610 minus 1,000 would be negative 390 watts per meter squared. I remember here that, right, Q double prime in this case is defined positive out, right, since the leading term here is the amount of emitted or the amount of outgoing radiation. And so this is our link to the more familiar world of energy balances and such, right? Because the idea is we're counting up all the energy going into it, G, and we're counting up all the energy coming out, J, and the difference is going to tell us how much energy is going towards actively changing the internal energy of that object. Okay, so that Q double prime is something we're going to just plug right into our energy balances to work through the more familiar equations that we've been dealing with so far. So we'll start on that on Friday. Until then, have a good one.